We're going to discuss a new physical quantity. It's really just a combination of some other ideas that we've already explored. So this physical quantity is called momentum. You've probably used the word momentum, you've probably heard about it, and maybe have a general idea as to what it is. But what it is, it's defined as the product of the mass and the velocity of an object, and it represents an object's total quantity of motion. So we give it the letter P for momentum, and it equals an object's mass times velocity. This really tells you pretty much everything you need to know about an object. And what's interesting about momentum is we can relate it to forces. So before we do that, just think about these two quantities, mass times velocity. First of all, what are the units? Well, we know the unit of mass is kilograms, and the unit of velocity is meters per second. So the units of momentum are kilograms meters per second. It sounds kind of strange, but that's what the units actually are. They're kilograms meters per second. And so what does this mean when we have the mass times velocity? Well, if you think about something that is very heavy, and I've used the example before of a train, and I'm going to use it again because I feel like it's a good one. So you have a train, and what do we know about a train? You have all these cars that are connected to each other, and it's very heavy. Now, a train might not move very fast. Maybe it hits a top speed of 60 miles per hour, but it's very, very heavy. So what does that tell you about the momentum of a train? Well, a train has very high momentum, and once it gets going, it's pretty difficult to slow it down. We remember from Newton's second law that force equals mass times acceleration. So this means that acceleration is equal to force divided by mass. So it takes a lot of force per individual mass. So if you have more and more mass, well, it's going to take that much more force to accelerate a train in whatever direction you're wanting to go, whether that's to speed up or to slow down. So there is this relation that, well, a train has a lot of momentum because of its mass, and if it's going, a reasonable speed, it's going to take it a very long time to accelerate from a certain velocity down to zero. And we can look at another example, which is that of like a little sports car or a race car. So a sports car is typically very light, but what do we know? Well, it can go very fast. So once it gets up to one of its top speeds, once it gets up to its top speed, well, it has a lot of velocity, even though the mass might not be very high. So the sports car also can have a lot of momentum once it gets moving very fast. So this is the general idea of momentum. It takes into account pretty much everything you need to know about a moving object outside of acceleration directly. And we're about to see here that it does also involve some ideas from Newton's second law. So if we look at just this quantity, this P equals mv, just keep that in the back of your mind. But let's start again from Newton's second law. So we're starting here from Newton's second law, and we know that force equals mass times acceleration. And if we're being precise, it's actually the sum of the forces if we have multiple forces. So what can we do with this? Well, we know that acceleration is the change in velocity over the change in time. So we can rewrite this as the change in velocity over the change in time. I've just substituted in the definition for acceleration. And okay, so this is a new way to write a force. And can we go anywhere from here to try to relate this to momentum is what I'm trying to do, is see if there's any relation here to this definition of forces from Newton's second law to momentum. Well, this mass isn't going to change. The mass is going to be constant. So I can put it inside of this delta, and it's not really going to matter because the mass isn't going to change. So what I'm trying to say is I can bring this down here, and we're discussing the sum of the forces, and that's equal now to, I'm going to say, the change in mass and velocity. But we're keeping in mind that the mass is constant. The only thing that's going to change is the velocity. And all of that is over the change in time. And what do we see? Just looking at this, well, if we look at our definition of momentum, we see that momentum is actually buried inside Newton's second law. So this can be rewritten now as the sum of the forces is equal to the change in momentum. I'm just substituting the letter for momentum in here because we have a mass times a velocity over the change in time. So a force is defined as how momentum changes over time. And if you think about that, well, if the momentum of this train is changing, obviously the mass is going to remain the same. Well, then the velocity must be changing. And if velocity is changing, then there must be some sort of acceleration that's happening. So forces and momentum have this interesting little relationship here where the force is equal to the change in the momentum with respect to time. Not just the momentum, it's the change in the momentum. It's how the momentum changes. So if I look at a momentum versus time graph, because I'm interested now in how momentum is changing, and I'm getting these graphs from page 56 in Experience Physics. So if I draw a graph here of momentum versus time, and it's changing, well, let's look at the slope of this graph because we know that the momentum itself is changing. So we can look at the rise over the run of this graph. So this is the rise, this is the run. And what is the change in the vertical position? So what is the rise in this case? So the rise is momentum final. It's going to be the final position of momentum on the graph minus the initial momentum. And this is just defined as delta P. And what is the change in the horizontal component of the graph? So this is the run, and this would be T final minus T initial. And you might see where I'm going with this. So this is delta T. So what is the actual slope then? So the slope is the rise over the run. So that is delta P over delta T, which is just equal to the sum of the forces. This is equal to the net force. And remember, we say the net force because if we're looking at an object and you have multiple forces that are acting on it, like if you have a box and it's being pushed by multiple people, and say there's 3 forces acting in different directions on the box, well, you combine the forces tail to tip, and then you can write the net force, or the sum of the forces, from the tail of the first vector to the tip of the last one, and this is F net, which is equal to the sum of the forces. So the change in momentum with respect to time is the force acting on the object, and hopefully that makes sense. If this train's momentum is changing, well, then the velocity must be changing. If the velocity is changing, we know that acceleration is equal to a change in velocity over a change in time. So if the velocity is changing, there must be an acceleration. And if there's an acceleration, there must be a force acting on the object. So that's how all those are connected. A change in momentum with respect to time means that there's a force acting on the object and that the object's accelerating and its velocity is changing. And if we compare two momentum versus time graphs here, one that is steep and one that is less steep, well, you can see that for this one, it is more steep. So that means that the change in momentum over the change in time is going to be greater. So this is going to result in a larger force. A larger force must be acting on this object to cause it to be steep relative to this other object. So this might be, we call this force 1, and then we have another force that's acting on this other object. These are two different objects. Well, then this one we can call F2, and we see that the force acting on the first object is greater than the force acting on the second object. So the steepness of this line tells you how large of a force you have. You're going to have a higher slope, a greater slope. It's going to be more steep. So the only other thing to look at then is that since we have this equation P equals mv, well, we know that velocity is a vector quantity. So if we're concerned about the direction, because sometimes you'll have a velocity at some angle or pointing off in some direction, then we do have to keep track of that if we're dealing with more than one direction. And so momentum also is a vector. So these are some things to keep in mind. Momentum's interesting, and it's especially useful when we're dealing with collisions of objects. So sometimes we'll be looking at how a momentum of an object changes before and after a collision, and we can solve some pretty complicated problems just using these simple principles that we've learned about momentum. Again, the change in momentum with respect to time results in some force. Because if the momentum's changing, well, then the velocity must be changing because we know the mass is staying the same. If the velocity is changing, well, we know that by definition that's acceleration. So therefore, there must be some net force that's acting on an object. If we see the graph and we see a steeper line versus a less steep line, well, then we know that a greater force must be acting on this top object versus the bottom object. The bottom object here would have a smaller force that's acting on it. Object 2 would have a smaller force that's acting on it compared to object 1.